Okay, have you tried this question? It's important. But it is not that difficult. So let's try this together. We are calculating the conditional probability of promotion given female. So female is the condition, and main event of interest is promotion. And first thing you can do here is to delete male observations. These guys do not satisfy the condition. Our condition is being female. So delete them, then it is easy. We have only two numbers, and among them, calculate the probability of promotion. So 36, it means promotion, is for promotion. So 36 divided by sum of them, the total number, which is 15%. Actually, we already calculated this in a previous slide, but it's now we would like to do it more formally. I believe it's straightforward. The idea is easy to understand. And one thing I want to say here is I would like to emphasize this. Many students are confused here about the order of the notation and the role of the two events. So think about this. Probability of P given F. This is obviously different from probability of female given P. I explained the difference, like F, the latter event is a condition, and the former event is, the first event is the main event of our interest. So the randomness is coming from the main event because the condition is already assumed to happen. So it happens with 100%. This happens with 100%. But we are interested in what is the probability for this guy, right? So now, like we calculated this number, probability of promotion among female police officers. That was what we calculated earlier. We had 15%. Now I am going to calculate this conditional probability, and I will show you this is different from the earlier one. So calculate this. Now the condition is promotion. We are choosing among the promoted and delete not promoted candidates. So then we only have this many observations that satisfy the condition. And among them, female is this many. There are this many female candidates who are promoted. So among these many observations satisfying the condition, you only have 36 observations that satisfy the main event of interest, right? If you do the math, it is 11%. So clearly different. So there is no relationship. So at this moment, probability of P given F is different from probability of F given P. So changing the order is not safe. Like be careful when you flip the role, switch the role between two events. They are different, totally different. And now let's formulate what we have learned in one formula. For any events A and B, the probability of A given B equals to the frequency of A cap B and divided by frequency of B. So FREQ means frequency, and this is the number of observations for each event. I defined frequency in the previous chapter. And then let's interpret this. So in the denominator, we have the frequency of B. This is the number of observations that satisfy B or number of observations that satisfy the condition, right? So in our data set, I throw away all the others, but I only use the observations, these many observations that satisfy our condition B. And on the numerator, on top, we have frequency of A cat B. So remember, the intersection means A and B happen at the same time. So it means a new event, a new compound event where A and B happen at the same time. But in this context, we already know that we are only using those observations that satisfy B. So all of the observations that we use already have B in those observations. B has already happened. So the numerator, this event means the event that A happens in addition to B. So B, we know B already happened, and we are looking for the cases where A additionally happens after B already happened. So this is exactly what we did in the previous slides, how we calculate the conditional probability. It's intuitive, and again, the main idea is the pool sizes are different. Previously, I told you the pool size difference was the main problem. So we fixed that problem by uh, using the pool size in the denominator. So this part is this intersection is divided by the pool size. So in the conditional probability, the pool size is adjusted. So it is a fair comparison now. Okay, so we defined conditional probability, and especially important is the distinction between condition and main event of interest. I'll give you another example with real data. In this example, the main research question is whether smoking increases the risk of high cholesterol or not. So I use real data, which is National Health Interview Survey from a recent one. The most recent one available to me was 2018. And in this data set, there are 7,888 observations. And I only collect two variables. In one variable, the respondent, the interviewee, was asked, have you ever smoked in your life? That was the first variable. And second variable is whether the respondent has ever been prescribed medicine to lower cholesterol or not. So the second variable is about cholesterol problem, and we define the events in this way. S stands for smoking, H stands for high cholesterol. Maybe there must be more formal, like Latin name, medical name for this symptom, or disease. I don't know. I will just call this high cholesterol. And by the way, the first step to start this analysis is to define the probabilities to compare. So we have to compare two probabilities as we did before. Structure is pretty much the same. We are comparing smokers and never smokers and see if they have different cholesterol patterns. Then, using the notation, what probabilities do we have to compare? It's very tricky, but this is maybe the most difficult question. Once you could define those probabilities, as you saw, calculating the conditional probabilities it's not that difficult. The idea is easy. So think seriously about this problem and try to rationalize your answer. And see you in the next video.